The next two chapters we cover in this course are going to deal with the topic of stereochemistry. And I've tried a number of different ways to do these lectures. But it doesn't seem to work real well with me trying to show you the three-dimensional models as I'm talking about them. So what I would strongly encourage you to do is to have a set model kit with you, and then as we talk about these, to actually build the models that I'm discussing. So stereochemistry is the part of chemistry that looks at the 3D aspects of molecules. And so a lot of this stems from the fact that carbon itself, as we learned in general chemistry, and specifically we're going to be almost always here dealing with sp3 carbons. Because all sp3 carbons have tetrahedral geometry and bond angles of 109.5 degrees. Now, why does any of this matter? Why should this three-dimensional idea of molecules being 3D make a big difference? Well, there's some different stories we can tell. Probably the most famous, the most well-known, and definitely the saddest, deals with these two molecules. So these two molecules, they're known as thalidomide. And thalidomide was a drug that was prescribed for pregnant women, back in the, I believe, 1950s as a treatment for morning sickness. Well, after a time, they discovered that there were some pretty significant birth defects, and they were being seen, from women who had taken thalidomide to treat their morning sickness. And what they eventually realized was that thalidomide can exist in two different forms. And so if you look carefully at these structures, the only difference in these two molecules is how the atoms are arranged at the center I've highlighted in yellow. Unfortunately, what they found was that the molecule on the left, while it was okay, the one on the right caused significant birth defects. And under biological conditions, because normally what I'm about to mention wouldn't occur readily, but under biological conditions, these two molecules are able to interconvert. And so because that was happening, these two molecules were interconverting. Even if you took only the one that didn't cause the problems, after a period of time, you'd have both of them present in your body. And so they ended up having to discontinue thalidomide's use. Another application of this, and this one's a little bit very different type of situation, but still illustrates this as well. Here are two molecules, both known as carbones. Again, the only difference between them is the way the atoms are arranged at that carbon. How different are they? Well, you can see some of the data between them. They're both oils, they have the same boiling points, they have the same densities, They have the same solubilities. All this stuff is the same. Yet if we gave you some of these molecules, you would pretty much instantly recognize the difference between spearmint and caraway. And so this idea of the three-dimensional shape, three-dimensional structure can have some pretty significant impacts. So previously we've defined this term constitutional isomers. Constitutional isomers are when we have the same formula but different connectivity. From here, we're going to start dealing with a larger class of compounds known as stereoisomers. Stereoisomers, same formula, same connectivity, different 3D arrangement. And specifically right now, we're going to start this part by talking about what are known as conformational isomers. So conformational isomers are ones that differ by a bond rotation. Because remember that single bonds, or at least most single bonds, are cylindrically symmetrical and in most cases have free rotation. So what I'd like you to do right now is to put together a model of ethane. And then I'd like you to start rotating about that single bond between the two carbons. And what I'd like you to think about is how many different conformational isomers can you possibly come up with? So at this point, pause the video and take a few minutes and put that model together. All right, so how many isomers or conformational isomers did you come up with? Because at least in theory, there are an infinite number of isomers, conformational isomers. Because if you take that bond and rotate it even half a degree, then that's a new conformational isomer. And half a degree more, or a quarter of a degree more. Every time you do that, is a new conformational isomer. But as we're going to see in the next video, we focus primarily on specific conformational isomers. In other words, some are more important than others. So before you open the next video, what I would recommend is that you put together models of ethane, propane, and butane, because we'll be looking at those in more detail.